In this example, we're looking at calculating the relative rate. And what that means is if we know the rate of either disappearance or formation for one component in the chemical equation, then we can simply use stoichiometry to calculate the rate of formation or disappearance of another compound. So what we do here is we need the balanced equation, and we have that here for a generic equation. And what we're given is the rate of disappearance for A, and we want to calculate the rate of formation of B. So we start with what we're given, and a lot of times when we're doing rate problems, we will write the rate like it was given here as molarity per second. But when you do these types of problems, it's a good idea to expand the units of molarity. And what I mean by that is to write them down as moles over liters, and that way all of the units will cancel as they need to. So we're going to do that. We're going to start with what we're given, which is the rate for A. So we have 0.007980, and it's moles per liter per second. So the moles is at the top, and liters and seconds are in the denominator. And this is for compound A. So we want to make sure we put that there. And then we write the stoichiometry, which is the relationship between the balancing coefficients. So we have 2 moles of A, so that will go in the denominator. So that way the moles of A will cancel, compared to 1 mole of B, which goes in the numerator. So we can cancel moles of A, and then what we're left with is moles of B per liter second, which is a rate, which are units of rate. Accounting for our sig figs, we have 4 sig figs in the rate that was given. Stoichiometry is always exact, and when we do the calculation to 4 sig figs, then we end up with 0.003990 molarity per second.